Hello everyone, this is Xiaoran from Rutgers University. Today I'm going to present our work towards flexible wireless charging for medical implants using distributed antenna system. Deep tissue wireless power transferring is crucial and sought after in many scenarios. For example, in-tissue wireless power could potentially help implant users avoiding surgeries for battery replacements, and flexible in-body wireless power could greatly improve the versatility and even functionality of controlled drug release. Further, the deep tissue power is a key enabler for in-body and body area communication, such as sending out monitored vital sign data or interfacing of electronics with human brain. Existing approaches for in-body wireless power transferring are mainly two categories: near-field and mid-to-far-field wireless charging. Near-field methods leverage the inductive coupling between transmitting and receiving coils, but the charging devices in this method have inherently large form factor and they will also suffer from coil misalignment. As such, it can be bulky and inconvenient. On the other hand, mid-to-far-field wireless charging method has relatively low charging efficiency, as well as the risk of overheating. Our method belongs to this category, and we focus on solving these issues by leveraging the advantages of wireless beamforming. Beamforming can greatly enhance the wireless charging efficiency by aligning transmitter's phase towards the target receiver. In traditional energy beamforming systems, the centralized phase array will form an energy beam towards the energy receiver. As a result, any obstacles blocking on the beam path would largely reduce the charging efficiency, and the blocking subject herself will receive even higher energy than the intended target receivers, hence suffering from overheating. By contrast, distributed beamforming spreads the energy transmitters around the target, but aligning the transmitter phases at the target at the same time. As demonstrated in the previous work, in distributed beamforming system, energy will be spatially focused around the target receiver as if forming an energy ball, which potentially avoiding overheating and blocking issues, which further translates to a safer charging environment. It is hence a natural choice for our deep tissue charging system. Implement distributed beamforming is, however, much more difficult than traditional centralized beamforming due to the fact that the transmitters are geometrically distributed, which means independent signal processing and inhomogeneous channel state information at each transmitter. Further, large signal attenuation in deep tissue makes obtaining CSI prohibited. We hence adopt a closed-loop implicit phase alignment method that requires no CSI and all transmitters can work fully independent. This method only requires the target receiver measure the RSS. The target receiver would iteratively guide the transmitters to build up the beamforming through feedback. In this realization example, we can clearly see the convergence process, and we can consistently achieve the optimal beamforming power using this method. Directly apply the previously mentioned distributed beamforming method is not going to work due to the unique requirements and challenges in our scenario. The first challenge is that the implanted devices are usually very low power. The previously mentioned method requires the receiver frequently compare the receiving signal strength and encoding the feedback signal to transmitters, which is power demanding in the long run. In our design, we offload all these computations to an out-of-body needle node using backscatter. This is feasible because the previously mentioned beamforming method only requires RSS as the target receiver. Please note, normal passive backscatter has a nonlinear input and output relationship. To solve this issue, we present a dual antenna monotonic backscatter design. Here is an example input and reflected signal from our backscatter. As can be seen, the reflected signal shares similar RSS as the input signal, but in a different frequency band. As such, we can infer this received signal strength as the implanted backscatter by using the reflected signal received at an out-of-body needle node, and let this needle node undertake all the following signal processings and feedback broadcasting. We therefore cool our system in and out. The next immediate challenge is the severe energy loss in animal tissues. Due to the two-way backscatter signal propagating, there will be less than negative 100 dBm received power at the out-of-body needle node, which translates to no CSI or even no RSS available for beamforming. In our design, we adopt chirp spreading as well as addressing its two sub-challenges to extract the minor signal change under the noise floor, and then feeding this extracted information to the implicit beamforming algorithm to build up the beamforming. We here show an example measured energy distribution inside of pork belly. We can clearly see an energy hotspot tightly formed around the target implants. Please note our system could achieve much higher delivered power in regular living rooms because they are usually smaller than our testbeds. And also we can easily scale up our system due to the advantages from distributed beamforming as we discussed previously. Thanks for listening. Please find detailed system design and experiment results in our paper.